In the 9th lecture on DSP, our topic today is discrete Fourier transform, which we abbreviate as DFT, and the discrete time Fourier transform we had abbreviated simply as FT in order to avoid confusion. In the 8th lecture, we had considered the question of convergence of Fourier transform or the existence of Fourier transform, and we said that absolute summability of the sequence is a sufficient condition, not a necessary condition. Similarly, squared summability of a sequence is also a sufficient condition. There are sequences which are squared summable, but not absolutely summable, and the example was 1 by n u of n minus 1. Then we said that there are sequences which are neither square summable nor absolutely summable, but their Fourier transform can be defined in terms of the analog delta function. And as an example, we took the Fourier transform of j omega naught n, and we showed in the reverse direction that it is 2 pi summation delta omega minus omega 0 plus 2 pi k, where k goes from minus infinity to plus infinity. We also gave you the basic table of Fourier transforms, that is, basic functions are delta n, u of n, the exponential e to the j omega 0 n, and alpha to the n u n. If you know these 4 transforms, then you can find almost all Fourier transforms of all familiar or known sequences. Then we took the example of the upsampler, and we showed that the spectrum is compressed. I would suggest that you carry out the example of downsampler and find out what happens to its spectrum. Okay. Then we took an example of an inverse Fourier transform which does not require integration. A bit of thought reveals that it can be done very simply by expanding cosine and sine in terms of the Euler relations. Okay. We discussed the properties of Fourier transform, and I think that is where we went a little fast. Linearity, time shift, frequency shift, convolution, modulation is multiplication in the time domain, and finally the Parseval's relation, which has an interpretation in terms of energy, that is, energy in the time domain is equal to the energy in the frequency domain. And then we talked about the symmetry relations. That is, if x of n is the Fourier dual of capital X of e to the j omega, then we showed that x of minus n is the dual of x of capital X of e to the minus j omega, and x star of n is the dual of a pair of x star of e to the minus j omega. I made a mistake yesterday, unintentional. There should be a negative sign. One of the students pointed this out. And then if x1 is complex, then real part of x of n is the Fourier pair of half capital X of e to the j omega plus x star of e to the j omega, no minus, and the imaginary part of x of n is 1 over 2 j capital X minus this. E to the power x star of e to the power minus j omega. Is that correct?
Yes.
Very good. That's it. Put a negative sign here. Okay. There are other symmetry relations which we want to mention casually because they are obvious, and it is that if x of n has the Fourier transform capital X of e to the j omega, which is x r plus j x j, then the even part of x n, the Fourier transform would be the real part x r. I am not writing the argument. The odd part of x n, the Fourier transform would be j times x j, and then x of e to the j omega, if I take the conjugate of this and I want to write an equality relationship, then instead of e to the j omega I should write e to the minus j omega. Okay. And if I take the real part is an even function, and therefore it is the same as x r of e to the minus j omega, that is omega changes to minus omega, it does not matter. The magnitude of x e to the j omega is also an even function, and therefore this is the same as magnitude of x e to the minus j omega, whereas the imaginary part of e to the j omega is an odd function, and therefore this is minus x j of e to the minus j omega. Agreed? And similarly the angle of x e to the j omega is also an odd function, and therefore if I change omega to minus omega, I shall get this as equal to minus angle of x of e to the minus j omega. These are the basic relations. This is a repetition, the real part is even, the imaginary part is odd, the magnitude is even, the angle is odd, but repetition is beneficial for learning to a certain extent. If it is repeated many times, then it loses its significance. And that brings us to the discrete Fourier transform. To understand the concept of discrete Fourier transform, let us consider a sequence. Discrete Fourier transform, I must tell you, holds only for sequences of finite length. Okay? Finite length. Suppose x of n is of length capital N, 0 to n minus 1. Then you know capital X of e to the j omega is simply x of 0 plus x of 1 e to the minus j omega plus etc. plus x of n minus 1 e to the minus j n minus 1 omega, where I have expanded the summation. Okay. Now on the left hand side the variable is e to the minus j omega. It is a polynomial in e to the minus j omega with capital N number of coefficients. Okay. So capital X of e to the j omega is completely specified if this n number of coefficients are specified. A polynomial is specified in terms of its coefficients. So for capital X of e to the j omega, which is a continuous function of omega, it suffices to specify capital N number of constants. These constants can be in the time domain or they can also be in the frequency domain. That is, if we take capital X of e to the j omega and sample it at capital N number of distinct points, that should be good enough. Capital N pieces of information are required to specify x of e to the j omega. This information can be in the time domain, that is x0, x1 up to xn minus 1, or can also be in the frequency domain. In other words, if I sample capital X of e to the j omega at n number of points, sample capital X at n number of points, distinct points, then we have n independent pieces of information, and that should suffice. So, what we do is instead of the time domain constants, we take x of e to the j omega k, where k varies from 0 to n minus 1. This must be capital N number of distinct points in the omega domain. That should completely specify capital X of e to the j omega. That is, a part of the information is adequate to reconstruct the full information. Usually this is not possible. From only a few parts one cannot construct the whole, all right. If I give you pieces of a furniture, 2 or 3 pieces, it requires a lot of research to find out what the total furniture is. I simply give you 2 legs of a chair. This could also form a plank or some other furniture, okay. But it is possible in this instance because the function itself has only capital N pieces of independent information. The information about omega, this is a variable x of 1 shall be multiplied by e to the minus j 1 omega, and therefore, this is not an information. Information is only in terms of the constants. So, this is the basis of defining a DFT. The sampling at k number of points can be uniform or non-uniform. Uniform sampling is preferred because this keeps life simple. What we do is to understand this, let us construct a circle, okay, where omega is 0 here and omega goes in the anti-clockwise direction. Omega increases in the anti-clockwise direction. So, it goes from 0 to pi plus theta and then 3 pi by 2 and then goes to 2 pi. Why do we consider omega between 0 and 2 pi? This is well known. What is the reason? Because capital X of e to the j omega is periodic with a period of twice pi. So, within one period, if I take capital N number of samples, then I should take samples at every 2 pi by n. The region, the angle 2 pi, the range 2 pi, we divide into n equal intervals. So, this will be my first sample. If I call this x of 0, then my first sample will be x of 1, and then another 2 pi by n, I get x of 2 and so on. I come up to 2 pi by n multiplied by capital N minus 1, because if I multiply by capital N I get x 0 being periodic, and therefore, I shall get here capital X of n minus 1. Okay. This picture defines what is Fourier discrete Fourier transform. In other words, our definition of discrete Fourier transform is capital X of k. This symbol is used for capital X of e to the power j 2 pi by n multiplied by k. Omega k, 2 pi by n is the basic interval, k times that. Okay. So, this is what we are using for the discrete Fourier transform DFT. This is defined as DFT of x of n, and this is obviously equal to summation x of n. It is the ft sampled at these values. So, instead of e to the minus j omega n, I shall have e to the minus j. The value of omega is 2 pi by n multiplied by k, then n, where n goes from, it is a finite length sequence. So, n goes from 0 to capital N minus 1, and this has to be computed for k equal to 0 to n minus 1. Okay. So, the sequence x of n, which is of finite length, and the sequence capital X of k, which is also of the same length, and k takes the same values as n, they are completely equivalent to each other. They are a 1-to-1 transformation. Why it is 1-to-1 can be shown by taking the inverse DFT of capital X of k, and the inverse DFT x of n is the IDFT of x of k, not a matter of definition. This was a matter of definition, we sampled. Okay. This is not a matter of definition, it is given by capital 1 by n summation x k e to the power plus j 2 pi k n divided by n, where k now goes from 0 to capital N minus 1, and it has to be computed for n equal to 0 to capital N minus 1. This is the inverse DFT. It is not a matter of definition, it follows from DFT, or if this relationship is given, then this will follow. Okay. This is a 1-to-1 transformation, and therefore, going either in the forward direction or the reverse direction should suffice. In the literature, for historical reasons, the quantity e to the power j 2 pi by n, e to the minus j 2 pi by n is usually given the symbol capital W subscript n. It is a bit unfortunate that negative sign is associated with this, but this is how it has gone in the literature, starting with the days of Cooley and Tukey. And therefore, we can rewrite our definition of discrete Fourier transform as summation n equal to 0 to capital N minus 1 x of n W n raised to the power k n. In a similar manner, the inverse DFT small x of n is 1 over n, do not forget this constant, 1 over n, k equal to 0 to n minus 1, capital X of k. Please distinguish between capital X and small x. Small x I write with curls, capital X is straight lines, two straight lines crossing each other. You might confuse between the two. This will be W n raised to the power minus k n. The values of k here are 0 to n minus 1, and the values of n here are 0 to n minus 1. This is a complete description of a finite length sequence, either in the time domain or in the frequency domain. Points to notice: capital X of k, in capital X of k, if I increment small n by capital N, does it change? No, it does not change. Therefore, capital X of k is periodic with a period of capital N. This is expected because capital X of e to the j omega is periodic with a period of twice pi. And what we have done is the interval twice pi we have broken up into capital N equal intervals, and therefore, capital X of k should repeat after capital N number of samples. But what is surprising is that small x of n, here also if I change small n to small n plus capital N, it does not change. Agreed? Small x of n therefore is also forced to be periodic, although it was not. We did not start with a periodic x of n, we started with a finite length x of n which does not repeat. That is x of n exists only from 0 to capital N minus 1, But if you carry out the computation, if you continue to carry out, it will exist beyond small capital N minus 1 also, and also on the left hand side. So, this is an advantage as well as a disadvantage. Disadvantage is that it has changed the character of x of n, it has made it periodic. But if you confine your attention to 0 to capital N minus 1, there is no aliasing, there is no distortion. Okay? And therefore, it is important that in DFT our range of vision, whether in the frequency domain or in the time domain, should be from 0 to n minus 1. We can't go beyond that. All right? This is an important point. Whatever operation we do on DFT or the sequence, delay, multiplication, convolution, whatever we do, we cannot go beyond capital N minus 1. We cannot go below 0. We must confine ourselves to this limit. It is a very important point which will come up in a few seconds. This formula, the inversion formula, can be very easily proved, and in the previous case I did not prove it in Fourier transform. Here let me indicate the proof. If you take, I will only outline the proof, I will leave the algebra to you. If we take k equal to 0 to n minus 1 x of k w n raised to the power minus k n, the trick is the same. I mean, in Laplace transform, Fourier transform, discrete time Fourier transform or DFT, the trick is the same. What we do is we replace x of k by its value in terms of the definition of DFT. That is, we write this as k equal to 0 to n minus 1 summation x of, now w n raised to the power minus k n, n is already here, therefore we use another dummy variable. We say L equal to 0 to n minus 1 small x of L w n raised to the power
minus
k L, not minus, right, w n raised to the power k L. Why did we change this? Because L is a dummy variable, we can't confuse with n, all right, small n. Oh, okay. Now, these two summations are independent of each other, and therefore we can interchange. So, if we interchange L equal to 0 to capital N minus 1 x of L, then we combine these two and sum up over k, because both contain k, agreed. So, we get summation k equal to 0 to n minus 1 w n raised to the power k L minus n. If you take the interpretation of w n as e to the power minus j 2 pi by n and sum this up, then you will see very simply that it is equal to 1 if L is equal to n. No, it is equal to capital N if L is equal. If L is equal to n, obviously it is 1 summed up capital N times, not n minus 1 times, because we started at 0, that is capital N, it is 0 otherwise. It comes from a function like 1 minus e to the power minus j 2 pi, an integer, divided by 1 minus e to the minus j 2 pi by capital N. And when L is equal to n, the integer becomes 0, so it becomes a 0 by 0 form, and you apply L'Hopital's rule to find this out. So, this is capital N, and it is very easy to observe that this summation exists only for L equal to n. Therefore, this must be equal to x of n multiplied by capital N, which means that x of n is equal to 1 by n, and we have we have proved it. This is the outline of the proof. You can carry out the algebra. The only point to notice is this: substitute Wn equal to e to the minus j 2 pi by n and carry out the summation. You shall get this result. So, this is a proof of the inversion formula. Enough of theory. Let us take some examples. Example. The first example that we take is the simplest sequence delta n. This is a one point sequence, isn't that right? One point. Suppose I want to find out its DFT, n point DFT, then what do? We pad zeros. So, we add how many zeros? N minus 1 zeros, and then capital X of k. If you put in the summation, delta n exists only at n equal to 0, and therefore, this will be simply equal to 1. All k between 0 to n minus 1. So, n point sequence, n point DFT is simply 1 1 1 1 1. Okay. Second example, suppose our impulse is delayed n minus m and we want to compute its capital N point DFT. Obviously, the delay m has to be between 0 and n minus 1. If it goes out, then we are not concerned. We cannot see anything beyond capital N minus 1. We must close our eyes to any range beyond capital N. Okay. So, if you apply the definition, then you get summation delta n minus m w n raised to the power k n. This is the definition, n equal to 0 to capital N minus 1. But this delta function exists only at n equal to m, and every other point it is 0. Therefore, the summation reduces to a single term w n raised to the power k n. That is it for all k between 0 and n minus 1. So, the sequence x k, the n point sequence will be 1 w n raised to the power m, w n raised to the power 2 m, and so on up to w n raised to the power n minus 1 m. This is the sequence. What was 1 1 1 1 for delta n, a delay makes it 1 w n to the power m, w n to the 2 m, and so on. Put m equal to 0 here, you get 1 1 1 1. Okay? It has to be. The third example is interesting. Third example is x of n equal to cosine of 2 pi r n by capital N, where r is a given integer. R of course has to be between 0 and n minus 1. R is an integer between 0 and n minus 1. And n, why it is confined to this? If we exceed, you will get the same result, and we cannot exceed. We should not go beyond capital N. This is our range of vision. The other things are forbidden regions. We cannot enter that region. Okay, I repeat this because it is a very important concept. In DFT, if you exceed capital N, then you are in trouble. You are in great trouble. Now, I find capital X of k by Euler's relation, that is, we put this as e to the j 2 pi r n by n plus e to the minus j 2 pi r n by n, that is w n raised to the power minus r n. Agreed? Agreed. I must multiply by half. it can be included. Okay. If equality sign is included, then obviously it is a sequence 1, that is it is 1 1 1 1, it is a gate. Okay. So, equality sign can be included. Yes, thank you Arpita, I know at least one name now, plus this would be W n raised to the power R n. Once we have done this, finding x of k becomes very easy. We get half summation W n raised to the power minus R n. I am not writing, okay, let me write n equal to 0 to n minus 1, then W n raised to the power, yes, k n plus summation n equal to 0 to n minus 1 W n raised to the power R n W n raised to the power k n. No change of sign. That is the definition. This is the sequence and this is the definition. How could we do this? Because DFT operation is linear. Okay? We broke up into two, the sequence, two inputs, and I find the output as the sum of the two. So, this becomes capital X of k is equal to half summation n equal to 0 to n minus 1 W n raised to the power k minus R n plus summation n equal to 0 n minus 1 W n raised to the power R plus k n. And once again that same summation comes. This is equal to capital N if k is equal to R, 0 otherwise. In a similar manner, this summation is equal to capital N k equal to minus R. Now, that creates a problem. We should not go into the forbidden region, but what value exists at k equal to minus R should also exist at k equal to n minus R, because it is periodic. Therefore, in the range of vision k equal to minus R or n minus R, and it is 0 otherwise. So, x k is equal to n by 2 for k equal to R, n by 2 for k equal to capital N minus R, and 0 otherwise. In other words, the cosine cosinusoidal digital signal cosine 2 pi r n by capital N has only two non-zero samples in its DFT. Let's see the plot. We have k, this is 0, this is R, I can't show, and this is n minus 1, the end, and this is n minus R. So, I have only two samples, all others are 0. You understand there are samples in between this. Well, I can do it like this. There are breaks 0, 1, 2, 3 etc. up to R. At R the value is n by 2, here also it is n by 2, R and n minus R. Had we been allowed to look to cross the forbidden region, then we should have another sample here at minus R. Okay. So, the basic DFT consists of two signals n by 2 and n by 2 and R at minus R. Although this is a forbidden region, I should not cross this, but I brought this into view for two reasons. One is that capital X of k is periodic, alright. So, whatever happens here must also happen here, alright. And the other thing is that cosine signal has only two samples of non-zero value, and these are at r and minus r. If you remember, cosine of omega 0 t, the spectrum of this has only two non-zero samples, and both of them are delta functions at plus omega 0 and minus omega 0. This is a reflection of the same fact. What we have done is we have taken the discrete equivalent of this, and we find instead of delta functions, that is impulses of infinite height, we get finite. This is the simplification afforded by discretizing the process. Okay. Our next concern would be a small comment that x of n, w n raised to the power k n, capital X of k, or small x of n equal to 1 over n, I forgot the summation, n equal to 0 to n minus 1, k equals 0 to capital N minus 1, and the other relation is capital X of k, w n raised to the power minus k n, small k goes from 0 to n minus 1, small n goes from 0 to n minus 1. The basic relationships DFT and IDFT. If you want to compute capital X of k, each capital X of k requires capital N number of multiplications. Okay? X of 0 multiplied by w n to the 0, although it is a trivial multiplication, let us consider all of them. We will see later how this simplifies. Then the next term, x of 1 w n to the power n 1, okay, and so on. Each x of k requires capital N number of multiplications, and this multiplication in general is complex. Each complex multiplication requires how many real multiplications? 4 of them, agreed. So, n complex multiplications, and to compute all the capital N number of points, you shall require n times n, or n squared complex multiplications. How many additions are required for each capital X of k? How many additions are required? N minus 1. N quantities added together requires n minus 1 additions, okay, and therefore the total number of additions would be n into n minus 1. And if capital N is something like 1024, then these quantities acquire astronomical dimensions, and therefore DFT, although it was known from Gauss's time, Carl Friedrich Gauss of electrostatics fame, Gauss's theorem or Gauss's divergence theorem in vector calculus. It was known from Gauss's time. Gauss used it, he did not know what is frequency, what is DSP, no, he did not know. He used it to compute things, to compute summations and with multiplications and so on, with Euler's formula, that is complex numbers and so on. He knew this. So, DFT in that sense was known, but nobody used it till about 1970s, early 70s, when these two gentlemen, Cooley and Tukey, Jim Cooley and I do not remember the initials of Tukey, they came out in 1965 or 66 with the so called fast Fourier transform, FFT, which is not a transform. first Fourier transform is an unfortunate nomenclature used by Cooley and Tukey and has gone into the literature like that. It is not a new transform, it is an algorithm for computing DFT or IDFT. You see, DFT and IDFT are of the same form, except for the change in sign of Wn, they are the same form, and therefore they came out with FFT with algorithms, numerical algorithms for computation of DFT and IDFT, which reduces the number of arithmetic operations drastically. In fact, we will show that instead of n squared complex multiplications and n into n minus 1 complex additions, what you require with FFT is of the order of n by 2 log n base 2, and this reduces the computations drastically. In fact, DSP was considered till that time as a very complicated matter due to two reasons. One is the lack of appropriate hardware. Hardware was very costly those days, but since 70s there has been revolutionary progress in hardware, in integrated circuits. That is one, and the second one is nobody used DFT because of the complexity of computation. You spend the rest of your life in computing a spectrum, then of course you are no good, okay? You have to do it fast, and with this the horizon of application of DSP widened like anything, and wherever you go now, it can be a power quality assessment or a power electronics equipment or a navigational equipment, sonar, radar, wherever you go you get FFT. The spectrum analysis, wherever spectrum analysis, even in numerical weather, the weather prediction, rainfall prediction, which of course goes wrong all the time, but that is a separate matter. They use DSP in the form of FFT. FFT is one of the main applications of DSP, and it has revolutionized technology in that wherever analog processing was done, even that is preferred to be done by DSP, and this is a monumental contribution by Cooley and Tukey. Some people say they rediscovered Gauss. Well, yes, they rediscovered Gauss, but they were the ones, they were the first ones to point out that yes, FFT, DFT can be used profitably in digital signal processing. We shall discuss FFT at a later date. The basic algorithms we shall discuss. There have been many variations of FFT, but one thing that you should remember very carefully is that FFT is not a new transform. It is a fast Fourier transform, it is simply an algorithm for DFT. FFT is not different from DFT, it is the way you compute the FFT. The next question that we address is the following. You have x of n, the samples are from 0 to n minus 1, okay. You have capital X of k, which is the DFT, samples are from k equal to 0 to n minus 1, okay. We said that capital X of k is a sufficient description of capital X of e to the j omega. Why? Because it contains n independent pieces of information. Capital X of e to the j omega also contains n independent pieces of information. The question now is, given x of k, how do you go to a capital X of e to the j omega? That is, if the parts are given, how do you reconstruct the whole? Okay. This process, in effect what we are trying to do is, suppose the samples are like this, what we are trying to do is to fill in between, agreed? Fill in between, and this process is known as interpolation. The question therefore is, given capital X of k, the DFT, how do you interpolate to capital X of e to the j omega? Once again I shall outline the mathematics, the detailed steps and other things which are very simple can be done by you and should be done by you. Capital X of e to the j omega is by definition small x of n e to the minus j n omega, where n goes from 0 to capital N minus 1, because x of n is of finite length. Now, we do the same trick. X of n we substitute by the inverse DFT, and then we interchange the limits of summation. Okay? We interchange the summations, n equal to 0 to capital N minus 1, x of n we write as 1 over n summation what did I use? We have to use k equal to 0 to capital N minus 1, capital X of k, then W n, let us write it as e to the power minus j, because I have e to the power here. Okay. Let me write instead of W e to the j 2 pi n k by n plus, thank you, multiplied by e to the minus j n omega. Now, I interchange the two summations, that is k equal to 0 to capital N minus 1, 1 by n I can take out, 1 by n, and then capital X of k, because the summation is over k, and the summation over n, both of these contain small n. So, let us combine them, n equal to 0 to n minus 1 e to the power minus j n omega minus 2 pi k divided by n. This is not a function of the form which will assume a value of capital N at some value, no, it is a continuous function, okay. And but the summation is a geometric summation, okay. We can find the summation as 1 minus e to the power minus j, instead of n we shall have capital N, therefore, we shall get omega n minus 2 pi k divided by n. I have multiplied by capital N. How come? This small n is to be substituted by capital N. So, capital N multiplied by omega, then capital N multiplied by 2 pi k by n. Objection overruled?
So, what are we doing? Summation?
Oh, divided by, yes, of course, we shall have that term e to the power, the common ratio as it is called in school days, e to the minus j omega minus 2 pi k by n. Okay. So, what we do is, now you can see that I have obtained capital X of e to the j omega in terms of capital X of k and this quantity. This quantity now can be put in a slightly different form, in a more convenient form. What you do is, you take e to the minus j, follow this step, I am not going to write it, e to the minus j omega n minus 2 pi k divided by 2 out. Then you get a function e to the j theta minus e to the minus j theta. Similarly, from here you take e to the minus j omega minus 2 pi k by n whole divided by 2. Then the denominator also you get a sign. You can combine these two exponentials, one in the numerator and one in the denominator, and the final result is the following. I will only write the final result. Capital X of e to the j omega is equal to 1 over n summation x k, k goes from 0 to n minus 1 e to the power minus j omega minus 2 pi k by n multiplied by n minus 1 divided by 2. You understand why n minus 1 divided by 2? Okay. then this multiplied by sine of omega n minus 2 pi k divided by 2, we had taken that factor out, divided by, what did you do with the 2j factor? They cancel in the numerator and denominator. So, we get omega minus 2 pi k divided by n whole divided by 2. This is the formula for computation of x of e to the j omega at any frequency, For example, suppose you have computed x of k between 0 and n minus 1. Suppose it is something like this. And so on. Okay. This is the gross spectrum of the finite length signal small x of n of length n. Now, maybe you are not happy with this, you are not completely convinced about the shape of the spectrum, you want to compute in between, okay? You want to compute at a dense set of frequencies. If you do that using this formula, it can be programmed in the computer, there is no problem. You can find its magnitude, you can find its angle and so on. Suppose you do that and find frequencies like this, in between, you are interpolating in between, okay? Then when you compute a sufficiently large number, then on the scope it will look like a continuous spectrum, agreed? And this is what is done in a sonar application, for example. In a sonar application, the signature of the enemy submarine, you take the DFT of that, all right, and you either use a very large number of points in the DFT so that these samples are very close together, or you see that is very costly and it also takes time. Suppose you want to compute at 2048 points, the computation requires a certain number of operations and each operation takes time. By the time you finish the computation, the enemy submarine may shoot you and sink your submarine, and therefore what one does is one starts with a smaller number of points. You see, one starts with typically, let us say 128 points, which can be done very quickly. Then you get an idea of the spectrum of the signature of the enemy submarine, and if this fits the known data about enemy submarine collected through confidential secret means, then you shoot at the enemy. If it does not, if you are in doubt, because it can be due to reflection from a nearby big fish like a shark or maybe a submerged ship somewhere or some other object, or could be even one of your colleagues' submarine. Okay? If you are not sure, then you increase it to 256, then you increase it to 512 till the spectrum makes you confident that it is the enemy or the friendly submarine. Okay. This is one of the major applications of DFT computed by FFT. The relationship capital X of k equal to summation xn wn raised to the power kn n equal to 0 to capital N minus 1. You see, this contains capital N number of equations, isn't that right? X of 0, x of 1, k goes from 0 to n minus 1. This is a compact way of writing the same equation, all right. Another way is to use matrices. Matrix is also a compact way of writing a set of capital N number of equations. And if I write this vector capital X of n minus 1 if I write this set as a column vector and this set x of 0, x of 1 as another column vector x of n minus 1, then obviously the multiplying matrix shall be capital N by capital N. It has to be a square matrix. The dimension here is capital N number of rows, 1 column, n rows, 1 column. So, this must be capital N by capital N. And the first row capital X of 0, which relates to x small x 0, small x 1, small x n minus 1. Obviously, the coefficients would be, if k is put equal to 0, the coefficients would be 1. So, it will be 1, 1, 1, 1, all right. Irrespective of the value of k, when n is equal to 0, the coefficient again is 1, and therefore, the first column should also be 1. Okay. For example, capital X of n minus 1 is equal to x 0 plus x 1 w n raised to the power n minus 1. The second row shall be w n squared and so on up to w n raised to the power n minus 1. And you can write the rest of the last one, for example, shall be w n raised to the power n minus 1 and so on w n raised to the power, yes, n minus 1 whole squared. Agreed? This matrix, this square matrix is represented by the symbol D capital subscript capital N. It indicates the dimension. The dimension is n by n, and Dn is this matrix, this square matrix, and therefore, in matrix form we write this as x vector is equal to Dn matrix multiplied by small x vector. And it is obvious that while the direct DFT can be written in matrix form, the inverse DFT can also be written in matrix form. It would be Dn inverse capital X. Agreed? And if you take Dn inverse, the only change, if you write the inverse relationship, that is connecting small x to capital X, the only change is that 1 by n factor comes, and instead of plus sign, negative sign comes, Wn to the minus 1 and so on and so forth. And Wn to the minus 1 is Wn star. E to the plus j pi by 2n is e to the minus j pi by 2n conjugate, and therefore, it follows that Dn inverse is nothing but Dn complex conjugate. So, if you know Dn, that is the only thing that you have to know, then you can do either DFT or IDFT. In other words, the same algorithm which is used for computing DFT can also be used for computing IDFT, and this is one of the versatility of the DFT operation. You know, in FT operation, one is a summation, the other is an integration. So, you have to have different algorithms. Integration is also done numerically. A digital computer cannot perform a continuous integration, but the algorithms are different. In DFT, the algorithms are the same. The only thing you have to change, no, I made a mistake here. Yes. The only thing you have to change is to introduce a scaling factor and change the power of Wn to negative. That is all. This is where I should stop today.